got our multiplication rule of counting. Or in other words, if a task consists of a sequence of choices, where there are P selections for our first choice, Q selections for the second choice, R selections for the third choice, and so on, then the task of making these selections can be done in P times Q times R different ways, or we are going to multiply. So it says we are going to choose a shirt and a pair of pants. So those are going to be our two choices. Those are going to be our two choices. Our first choice is going to be our shirt. Our second thing we're going to be choosing from is pants. My goodness, my pen does not want to work very well. All right. So then I'm going to keep reading. So we're going to choose a shirt and a pair of pants from a selection that includes a red shirt. So there's one, a blue shirt, there's two, and a green shirt. So we have a total of three shirts to choose from. We then have a pair of khaki pants and a pair of jeans, or we have two pairs of pants to choose from. So when we want to figure out how many pairs of or how many outfits are possible, we are going to multiply. We're going to say 3 times 2, where we end up with a total of 6 outfits that are possible to choose from. So there are 6 different outfits possible. So let's look at something that's a little bit more real world to a lot of us. We're going to look at getting a username, So we're going to suppose that a local network requires usernames to have exactly 5 letters followed by a digit. And we're going to say that upper and lowercase letters are going to be considered the same. And we want to know how many usernames are possible. So before we really get going with this, the first thing we want to remember is we need to know how many letters are in the alphabet. So when we talk about letters in an alphabet, we are talking about the 26 letters that are possible in our alphabet. So there are 26 letters in the alphabet that we could choose from. Then when we talk about digits, so this one's a little bit harder. Let's remember the entire sample space for digits would be the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are all just one singular digit. And if we were to count, what you will see is that we have a total of the number in our sample space. We have a total of 10 digits there. So now that we've got that information, we're able to continue on to solve this thing. We have our two different selections that we're going to make. We're going to select between a letter and a digit. Then it told us here a second ago that we are going to have exactly 5 letters in our username. We're going to have exactly 5 letters. So I'm going to put 5 spaces for letters. We have 1, 2, 3, 4, 5 spaces for our letters. Then after our letter, it's going to be followed by exactly one or a singular digit. 1 digit. Then what we figured out earlier, what we wrote down is when we talk about letters, we have 26 letters to choose from. Oh my goodness, my pen. Let's see if I can type the number 26 and just copy it a few times. Teams. 26. So when we talk about letters, we have 26 different letters to choose from in the alphabet. And we're going to have those 26. We're allowed to have repeats. So we're going to have those 26 letters to choose from 5 different times. So these are all of our letter spaces. Then when we talk about numbers, we're talking about those 10 digits that we have to choose from. So we have those 10 digits. Then it says up here by definition that after we have those choices and we tell how many of each choice we have, we're going to multiply these together. So I would say 26 multiplied by 26, multiplied by 26, multiplied. So I'm going to pull open Desmos. I'm going to bring it over here. I would say, for instance, 26 times 1, 2, 3, 4, 5 different letters multiplied by that one digit. And we have 118,813,760 different possibilities for usernames with exactly 5 letters and one digit where repeats are allowed and uppercase letters and lowercase letters are considered the same thing. So now think about all the different usernames for all of the different Googles and Yahoos and whatever you might be on. So there are a lot of different combinations with a lot of different length that we could certainly come up with for usernames. The next type of technique we're going to talk about is the factorial. And in mathematics, the exclamation point represents a factorial, where in factorial means that you take the positive integer in and multiply it by all the positive integers less than it. So for example, if I wanted to calculate the factorial of 6, so 6 factorial, right here I would say that is 6 times 5 times 4 times 3 times 2 times 1. I could put that into Desmos, so let me bring Desmos back over. So if I put that into Desmos, 6 times 5 times 4 times 3 times 2 times 1, I would get a total of 720. You could also, what you'll notice here in Desmos is if you are using your keypad, what you can do is you can hit the number 6, hold down Shift and hit the number 1, just like you're using an exclamation point for an English paper. When you do that, that is our factorial in our calculator, or once again, it gives me 720. One more way to get this factorial in Desmos is once again, you could hit the number 6. You can then over here hit function, F-U-N-C, function. Then down here, we get that factorial button. I can click it, and I once again get my 720. So our answer here would be 720. Now, by definition, 0 factorial is equal to 1. And the application for factorial is a collection of n things that can be arranged in n factorial many ways. So if we want to find the number of ways that 9 players on a baseball team can line up for the national anthem, or how we can arrange those 9 different players, what we're going to do is we're just going to say 9 factorial. We're just going to say, my pen will work, 9 factorial. I would bring Desmos back over. In Desmos, I would say 9. I can click this factorial button, and I end up with 362,880 possible ways those 9 players could line up for the national anthem. So once again, I would end up with 362,880. The next thing it asks is how many ways we can rearrange the letters in the word painter. We can rearrange the letters in the word painter. So I'm going to count. I have 1, 2, 3, 4, 5, 6, 7 unique letters in the word painter. So I'm going to say 7 factorial. When I do that, once again, I'm then going to bring over Desmos. 7 factorial will end up giving me 5,040 different ways I can arrange the letters in Painter. I've got 5,040 different ways I can arrange the letters in Painter. The next type of counting techniques we're going to talk about are our combinations and our permutations. So combinations and permutations tell us how many ways there are to select our items out of a total of n. So our n should always be our larger number. It is our total. And then we are going to select our ways out of that total. We have two big differences between the two. Permutation is when the order matters. Combinations are when order does not matter. And that's going to be on us to decide in most of these problems. But then once we do get down whether or not the order matters, we figure out the total and we look at how many we're selecting, we will be able to use Desmos to figure out these permutations and combinations. So while we do have these formulas here, we are going to want to get familiar with using Desmos. Oh my goodness, let's try that again. I'm going to try to type it. My pen just sometimes it wants to work and sometimes it doesn't. But we are going to use Desmos. So if you have a TI-84, you can certainly use your TI-84 and you do not have to use the formulas, but I am going to show you guys Desmos. I'm going to show you guys Desmos. So let's say after we've looked at some problems, we do see that we need to calculate either 20P6 and 20C6 using technology. So what we're going to do is we're going to open up Desmos. Once we get into Desmos, we are going to click on FUNC or function. Once we get there across the bottom, so you guys are going to see across the bottom when I click on function, we have NPR, NCR, and our factorial. So depending on which one you will need, you will click either NPR or NCR. You will put in the numbers like above, such as 20, comma, 6. So as we do this using Desmos, what you will notice is we will put it in, see if I can get this to work, NPR. We will put in first the N and then comma your R and then close that parentheses. So the N and the R will be your inputs. Once you put those inputs in, it will give you the count. So let's take a look. When I click NPR 20, comma 6, I get 27,907,200 different possible ways. Let me just copy and paste. It sure will. Let's now do the same thing for NCR, or our combinations. So I'm now going to say in Desmos, NCR, parentheses, 20, comma, 6. Let's bring up Desmos, NCR, 20, comma, 6, close that parentheses, and I get 38,760. 38,760. So we are going to do most of this using technology. What is going to be the most complicated is in a little bit, we are going to look at the word problems, and we do have to figure out if order matters, where we use permutations, or if order does not matter. In that case, we would use combinations. So this is one of those type of problems. We say that there are 50 members of a local club. So what we've just figured out in that first sentence is that our N is going to be 50. Our N is going to equal 50. It then says they must select a president, a vice president, and a secretary. And they want to know how many different slates of candidate are possible. Well, we've just selected 3 choices. There are going to be 3 choices we choose from. So then the last step is figuring out if order matters, or if being president is different than being secretary, if you'd rather be picked first versus second versus third. And in this case, yes, order matters. Because order matters, we're going to use a permutation. So that means we're going to say in Desmos, in PR, parentheses, 50, comma, 3. Make this a little bit bigger. So we're going to put that right into Desmos. So once again, I would hit this guy down here, 50, comma, 3, and I would end up with 117,600 different possible ways that these top 3 or that out of 50 members of a local club, we could get a president, a vice president, and a secretary. So we are going to form a subcommittee of 4 people. So this next one, we are going to form a subcommittee of 4 people. And as we are looking at that subcommittee of 4 people from those original 50, we are going to see how many are possible. I apologize. I'm trying to figure out where that 47 came from. That 47 is not in my notes. So give me 1 second. I do apologize to make sure my notes are fitting your notes. It's because, okay, sorry, y'all. I just had a small glitch of a moment. I apologize. I apologize. We already picked three. This is not a different question. Oh my goodness. I'm going to see if I can rewind and take that out. So there were already three people picked. I was looking at this four, but we aren't on new. Same looking at the same question. So we started off with those 50 people. Then three people were picked for president, vice president, and secretary. So because 50 out of those 50, three have already been picked, these 47 are who are left. So we now have 47 students basically left to be picked from. Out of those 47 remaining, there we go. Out of those 47 remaining, we want to know how many different ways there are to pick four people to be put on the rest of these subcommittees. Now, as we get put on these subcommittees, it doesn't matter if you're the first one to be put on the subcommittee or the last one to be put on the subcommittee. So as we are choosing these these groups of people to be put on a subcommittee, what we are now going to say is order does not matter. If I can get my pen to write. Does not matter. All right, because the order does not matter, we are going to choose NCR. We are going to choose NCR. I'm going to go back to typing. Didn't even change to black. Goodness. NCR. We're going to put in 47, comma 4. As we do that, I'm going to open up Desmos. We say NCR down here at the bottom, 47, comma 4. And I end up with 178,365 different possible ways to form that subcommittee of four people. Next, we're on a brand new problem now. So we're no longer starting with that 50, which is what I got confused on last time. So we are now starting a whole new question. And this time we're going to suppose that 40 cars start the Indianapolis 500. The first thing I want to make a comment on is not everybody knows this, but this guy right here, the Indianapolis 500, is the name of the race. So that 500 does not mean anything in this math problem. That 500 is the name of the race. So we're going to start with 40 cars. So that's my N. That's my N. It then wants to know how many different ways can the top three cars finish. So we're going to be selecting the top three cars. And then the question is, does order matter or not about those top three finishers? Well, when you're running a race or driving a car for a race, usually you want to come in first place. First place has more winning money. It has the better prizes. You get to be on Wheaties boxes sometimes, whereas second and third place usually don't get those cool gifts and those cool prizes. So when we are talking about finishing a race or running a race, we do care about the order we finish. So in this case, order matters. Because order matters, we do want a permutation. So we're going to say NPR 40. Come on. 40, comma 3. Didn't change colors, but y'all get the idea. So I open up a Desmos. I would say NPR 40, comma 3, and I end up with 59,280 different possible ways that those three cars could win that race. 59,280. 59,280 different ways. Next, it says how many simple random samples of size 7 can be obtained from a population whose size is 60. So we are starting a brand new problem. So as we look at this problem, our n is going to be our larger number, or our 60. Our r is going to be the number of different sizes or different samples we can obtain of size 7. So our r is going to be 7. In this case, as we look at it, what you will see is that order doesn't matter. We're just going to make a couple different groups. So order does not matter. When order does not matter, we are going to use our combinations. So I'm going to say NCR parentheses 60, comma 7 in Desmos. I end up with 386,206,920 different ways to get simple random samples of size 7 from a population of size 60. So now we're going to look at how we can do some probabilities using these combinations. We're going to look at some probabilities using these combinations. So let's say there are 10 green marbles, 12 red marbles, and 8 blue marbles in a bag. It first wants to know how many different ways are there to pick 5 marbles out of the bag if order does not matter. So before we can really get going, we need to know our total. Remember, n is the total number of ways. Or not total number of ways, but it's the total we are looking for. So I'm going to say those 10 green marbles plus our 12 red marbles plus our 8 blue marbles, or I have a total, even though that should be blue. There we go. Or I have a total of 8 plus 12 gives me 20. 20 plus 10 gives me 30. I have a total of 30 marbles to choose from. So my n is going to be 30. It then says we are going to pick 5, or we are selecting 5 marbles. So my r is going to be 5. And because order does not matter, they are telling us once again that order does not matter. We are going to use a combination. We are going to use a combination, or NCR. That means our combination is going to be 30. Oh my goodness. 30. We're going to try that again. Comma 5. Looks a little bit better. We're going to throw that into Desmos. I'm sorry all my colors are messing up today. I'm going to pull open Desmos. I'm going to say combination 30 comma 5, and I end up with 142,506 different possible combinations to pick those marbles. 142,506 different ways to pick those marbles. So now they want to know, if we do pick 5 marbles out of the bag, what is the probability that 3 of those marbles are red and 2 of the marbles are blue if order does not matter? So we need to go back to a lot of our rules of probabilities. We know that probabilities of event E would be the number in E. Oh my goodness. Let's try this again. The probability of event E is equal to the number in event E divided by the number in our sample space. So I'm going to make this look better in a second. So we're going to say divided by the number in our sample space. We also know, or let me look at it a different way. Let me look at it a different way. I don't like the way I just wrote that. Let's go back and let's say that the probability of A over B, instead of saying our sample space, let's say the probability of A is equal to the times the number of times A occurs all over the number of trials, oops, the number, the total number of trials of the experiment. So in part A, we just figured out the total number of trials in the experiment. We know the total number of trials in the experiment is the 30 marbles when we pull them 5 different times. So we already figured that part out. That was A. But now we need to look at the number of times A occurs. Well, what they want is they want the probability 3 are red and 2 are blue. Well, we also know and over here means multiply. We know that guy means multiply. So what it really wants here is it wants the probability that 3 are red and 2 are blue. So we're going to need the probability that 3 are red before we can really figure this out. We first need to figure out the probability that 3 are red. Well, if we know, so let me now do that. If we know we have a total up here of 12 red marbles to choose from, We have a total of 12 red marbles to pick, and we are selecting 5 altogether. Then we have 12 out of 5 possible ways to select a red marble. So I'm going to say 12. Oh, let me start that again. We're not selecting 5. We're selecting 3. I'm silly. We're picking 3 are red. So we have 12 red marbles to choose from, and we are going to pick 3. Or in other words, I'm going to have an N of 12, and we are going to be picking 3. Then we are going to be able to pick, let's just say instead of probability, let's do the number. Let's do the number of red we could choose from. Well, then we would end up having NCR 12, comma 3. Then we need to look at the total number of times 2 blues can occur. Well, we have a total of 8 blue to choose from. And we want 2 blues. So we know that our N would equal to 8 and our R would equal to 2. So to be able to find the count of how many blues we would be able to choose from would be NCR parentheses 8 comma 2. I'm now going to find both of these using Desmos. So the total count for our red possibilities, when order does not matter, would be 12 comma 3. My total count for my blues would be NCR 8 comma 2. So the total number of possibilities I have to pick a red marble would be 220. The total possible ways I have to pick a blue marble would be 28. So now that we have all of our counts, what I can do is I can say that the probability of picking 3 marbles that are red and 2 are blue would be my 220 choices for my red multiplied because of the word and the 28 choices for my blue. And then it's going to be all over because a probability is divided by the total. We're going to say that is all divided by the total count for picking 5, or part A, which would be 1,400 or 142,560. 142,560. Oh, my bad, not 60, 06. There we go. 142,560. So I'm now going to use Desmos. I'm going to say in Desmos, parentheses, 220 times 28, close that parentheses, say divided by 142,506. I get a probability of getting 3 red marbles and 2 blue, if order does not matter, out of my bag of 30 marbles would be 0.0432. 0.0432. We could also put it all into Desmos under one step if we really wanted to. We could have said fraction bar NCR 12 comma 3, close that parentheses, say multiply by NCR 8 comma 2, close that parentheses, divide by NCR 30 comma 5, and we get that same decimal. That is the end of our 4.4 counting techniques.